So the influence measures are things like the DF betas, that sort of thing. So let's just go through some cases. Here's a nice case right here. There's no regression relationship between x and y, but we have this one outlying point out there, right? So I just generated random bivariate noise and then threw a point way out there. So we get this regression line just by virtue of that. So this point has huge potential for influence that it actually exerts. Okay. That's the code. So I generated one point that was 10, 10, and then the x's and y's were otherwise just standard normal noise. R norm n, independent R norm n. That C isn't necessary right there. And then I put the AB line is the fitted line in there. So the point 10, 10 has created a strong relationship where there shouldn't be one. So it's showing a couple of the diagnostic values. That point, obviously, if you look at the DF betas, right, which are exactly the so the DF betas are the coefficient, the difference in the coefficients between what you get if you leave that data point in versus you take it out. And so you can see, obviously, the slope coefficient changes dramatically if you include that one point that's driving the whole relationship versus you take it out. The hat values are, as always, a measure of potential for influence, and so this guy has, of course, a giant hat value. Okay, so now let's consider a case where there is a regression relationship, and see in the point, which is sort of outlying here, which is sort of outlying in terms of its x and y values, but still quite well fits the regression relationship. So in this case, if we do the DF betas, you can see that that point is generally in line with the other ones, not outrageously so, but the hat values, its hat value is quite a bit bigger than a lot of the other data points. But notice, just one thing I want to point out is this outlier is only at the x's and y's are bivariate normal on that kind of scale if you look at the code, but this guy's only at say 5.5, whereas this other one was quite far out there at 10.10. That's why the hat value for that other one was so much larger. So let's go through an example of looking at residual plots. And Stefanski in this American statistician paper had this great kind of startling example, several examples, and he created this mechanism for creating them on why it's useful to look at residual plots. So here's the data. I grab it from his server, and don't everyone hit his server. Instead, kind of read at the same time. Read the paper first, and then pairs just does all pairwise scatter plots. All right, so here's all the variables, and you obviously don't see very much in the pairs plot. In this case, there's a ton of overplotting. If you do a standard linear model where it takes this first variable and regresses it on everything else, and then just grab the coefficient table, you see a bunch of highly significant p-values. Imagine if you were to stop there. Okay, but there's clearly an evident aspect of some pattern in the residuals, because if you say fit the model and then plot the residuals versus the predictive values, which if you have a multivariate relationship, if you have a multivariable regression model, it's often useful to put the predicted values versus the residuals. In this case, there's obviously some sort of pattern there. That's the O'Reilly owl. So let's look back at the Swiss data and see what these different plots are trying to accomplish a little bit. So the residuals versus the fitted values, those are, you're looking for any sort of pattern. Same thing with the fitted values versus the standardized, this scale location plot here, where it's plotting a function of the standardized residuals. The normal QQ plot is, you're trying to figure out normality of the errors by plotting the theoretical quantiles of the standard normal distribution by the standardized residuals. And it's a little bit difficult to tell because of the scale, but these are the labeling of the points of some of the provinces. And then residuals versus leverage, that's where you want to look at the comparison of fit at that point versus the sort of potential for influence of that point. So this is also a very useful plot to look at. I would also suggest for everyone in the class to go through the example of looking at the DF fits and the DF betas and Cook's distance for all of these for this data set. And what you're interested in looking at are whether or not these measures, whether or not one of the particular provinces seems influential or has a particular kind of large effect, and then you would want to sort of dig into that data point in specific.